The first one is by Sara Bernardini. Sara.
Hi, this talk focuses on autonomous search and tracking via temporal planning, and it's a joint work with Maria Fox, Derek Long, and John Bocles. So SAT mission involves a UAV searching for a mobile target and tracking the target after it has found it. Search and tracking has a number of practical applications, for example, in search and rescue missions and surveillance missions. In our case, the observer is a single fixed-wing UAV equipped with an imaging system that can observe the target, and the observation is prone to error and interfaces. And the target is a vehicle traversing a mixed urban, suburban, and rural landscape, and we assume that the target has a destination and follow the road networks and doesn't exhibit any significant evasive behavior. Any search and tracking mission has two different phases, constantly interleaving. Tracking, that is when the target is visible and the UAV flies in a standard pattern over the target, observing its progress. And then search, that is when the target has been lost, and so the UAV flies a series of maneuvers that are intended to rediscover the target. And so let me focus first on the challenges that we faced while handling this application of search and tracking. So first of all, we ask ourselves whether planning is relevant in this context and if we can see an application of search and tracking as a planning problem. So at first sight, one might think that tracking is a planning problem, in particularly temporally extended goal problem, when the goal is to keep the target in view as long as possible. However, as we consider the problem more in depth, we realize that tracking the target where it is in view is more like a reactive control problem, since we don't know the intention of the target. And however, it's when the target is out of view that we need to plan a rediscovery strategy to relocate the target. So our approach is to track the target reactively while it is in view, and then to plan a recovery strategy when the target is out of view. And so we model search as a planning problem. The second question was, is search a non-deterministic problem? Because, of course, there is an uncertainty relating to the fact that we don't know the location of the target, where it is going, and also we don't know whether the target will be reacquired, even if it is visible to the spotter. And actually, we think that search can be seen as a deterministic problem because we can work under the assumption that the location of the target is unknown, so we can plan for the UAV under this assumption, and then whenever this assumption fails, which is that we rediscover the target, the plan becomes irrelevant and we can abandon them. So basically, we want to model the search phase as a deterministic problem. So the challenge was actually in mapping the search and the search phase into a planning problem, and then how to map back a plan into a series of execution commands for the UAV. So in this talk, I will focus more on what we found more challenging. So as I said, how we formulate the search as a planning problem, how we actually built the initial state and the goal for our planning problem, and how we use the plan to operate the UAV. I will just skim over what we found easier, like to model the domain actions and the actual planning phase, as we used an off-the-shelf planner. So, as I said, tracking is managed by a reactive controller, and the flight path of the UAV during the tracking phase is just a circle of fixed radius centered on the target. And as the target moves, the circle moves with the target, and so the flight path is just a spiraling pattern over the ground. So what happens if the observer loses the target? So for a short period after losing the target, the UAV can simply track the predicted location of the target. But after a period, it is necessary for the UAV to have a more systematic strategy to rediscover the target, and in particular to direct the search in specific places. And we use standard search patterns to look for the target, and in particular spiral patterns to cover urban areas, and low-mowers patterns to cover rural areas, and also more elongated areas corresponding to, for example, major roads. So why we want to use these search patterns? Of course, another possible approach that in fact is used by a number of state-of-the-art approaches to search and tracking is to estimate the probability density function of the target, and then solving the search control problem in a greedy fashion. However, this strategy works under a number of assumptions, which are that we deal with a small geographical area, we have a short-term mission, and the target is stationary, or if it moves, it doesn't exhibit unintentional behavior. But these assumptions are not satisfied in our case, and so if we try the probabilistic approach, it becomes quickly intractable, and so this is why we are actually trying a novel approach to search and tracking, because we want to deal with big geographical areas, long-term missions, and also our target has unintentional behavior. And the second motivation is that the behavior of a UAV while following a standard search pattern is predictable, well understood, verifiable, and so this increases the trust towards autonomous vehicles. So, our strategy is that when the UAV has lost the target, it flies across the terrain in search for the target, and it executes a sequence of search patterns that can be chosen in such a way to optimize the likelihood of rediscovering the target. So basically now the question is, how do we actually distribute these search patterns over the terrain in order to maximize the likelihood of rediscovering the target? And so this is just when planning comes into play, because we see the selection of search patterns as a planning problem. And in particular, what we do for each search pattern, we assign a reward, where a reward is a value corresponding to the expectation of finding the target in a search of the area corresponding to the pattern. And then the planner chooses the sequence of search patterns that maximizes the accumulated expectation of rediscovery. So rewards can be assigned to patterns on the basis of historic data, which is where the target was when it was seen the last time, and which was its average bearing. And then also on terrain structure and the road network. In our case, the state is associated with information about the position of the UAV, the last known location when it was seen the last time, and also the status of the search patterns. And the actions are simply navigations between different patterns and the execution of the patterns itself. Again, as I said, we see this as a deterministic problem, because the patterns can be selected under the assumption that the target is not found. And if the target is found, the observer will go back to the tracking phase, so the plan becomes irrelevant exactly when the assumption fails. So here is how the domain looks like. It's a simple domain, so we have like a fly action to go from one waypoint to another, and then we have an action corresponding to each search pattern. And in particular, all these actions have a similar structure. So we have an entry point and exit point for the pattern, and then we have a duration. So these are durative actions, where the duration is the actual computed value for the execution of the corresponding search. And then the pattern is active only in a period during which the target could plausibly be in the area covered by the pattern, considering the speed of the target. And then the effect of the action are, of course, to move the position of the UAV, and also to increase the total reward. And so this is the crucial effect. Then the goal, basically the problem has no goal, but the plan metric measures the value of the plan in terms of the accumulated expectation of funding the target. Now we go to the more interesting part, which is how do we create the initial state. Basically, in choosing a good sequence of search patterns to execute, we want the planner to reason only about a finite subset of promising patterns. And during the construction of the initial state, we deal with two main tasks. Identify the candidate search patterns, and the planner will reason only among these patterns to choose a strategy to rediscover the target, and then to assign an appropriate reward to each of these patterns. And so let's start with the first task, which is identifying a set of promising candidate search patterns. So what we do, we select a subset of the general search area in which the target is more likely to be rediscovered. And so we have a circular sector that is centered on the last known location of the target, and then extend outwards with the symmetry axis aligned with the average bearing of the target over the period during which we could observe the target. Then we sample points in this selected area using probability distribution laid over the area, and based on the density of the roads in that area, the terrain type, and also the distance from the last known location of the target to that point. And then for the most promising points, we select which pattern we want to use in that point. So we favor spirals, as I said, to cover more urban areas, and lawn mowers to cover rural areas or major roads. Now that we have the search patterns, we have to assign a reward, and we use a time-dependent function for that. In particular, we calculate a window of opportunity for the pattern by considering the shortest and longest time of arrival for the target in the area covered by the pattern, and we use this as limits to set a value function. So the reward is 0 outside, and then inside the window as the shape of a lifted Gaussian distribution. And we deal with these rewards in the initial state by using time initial fluence. This is a simple fragment of an initial state. As you can see here, we have names for the different search patterns. So actually the planner reasons in an abstract way about this pattern, doesn't deal with the coordinates or this more low-level information. And then here, for example, we have have a peak reward of 1,732 at this time. And then basically the reward goes to 866 inside the windows of opportunity and goes to 0 outside. So we built the initial state. So we have now everything we can plan. We use Optic, that is an anytime cost improving search. And so the planner finds first solution very easily and then improves on this by adding further search patterns to the plan and trying different collection of patterns. And we gave to the planner a time bound of 10 seconds. And usually, on average, Optic produces 6 plans in this period. And for now, we have a static policy, meaning that we freeze time while we are planning. However, we then want to replace this static policy with a learn policy, as I will say when I present future work. So, in order to evaluate the behavior of our plan search approach, we developed a simulation that you might have seen yesterday. And this was done in consultation with our industrial collaborators. So the main abstraction in the simulation is that we don't consider control of flight surfaces and altitude. And we have an area of 100 kilometers squares, with Glasgow and Edinburgh approximately defining the lower corners. And the target follows a path acquired by Google Maps using a configurable origin and destination. And the simulation integrates the planning phase. As you can see here, we show the candidate search patterns, and here is the planning going on. And then when the planner has finished, we show the best plan. In this case, these 4 were selected. And then the UAV starts following this set of search patterns until it rediscovers the target when the plan is abandoned and the tracking phase is resumed. So we show some experimental results. We compare our plan-based policy with our fixed policy that was suggested by the our industrial collaborators. So we track the target, this fixed policy track the target until it's in sight, then continues to track the predicted location of the target for about 3 minutes after the target is lost, and then it executes a fixed sequence of patterns. And for our experimentation, we considered 20 routes, and we run the simulation 1,000 times per each strategy. And here you see that basically the metric is the proportion of runs in which the target is tracked to its destination. And so the green is the plan-based strategy. And so you can see that the plan-based strategy is consistently better than the fixed strategy, and the static policy has an overall success under 50%, while the plan-based search has a success above 60%. And then here another interesting result. So in this case, we are looking at the probability distribution over time of relocating the target after losing it, considering only cases in which it was successfully relocated. And as you can see, our plane-based policy is much more robust than the fixed policy, because we can actually manage to rediscover the target even after half an hour that has been lost, while for the fixed for the static policy, it finds the target after has been lost for 10 minutes in less than 4% of the cases. So now we are extending our simulation, considering obstacles, and obstacles introduce new search patterns, like, for example, patrolling the entire obstacle or patrolling an edge. And obstacle can correspond to different things, like no-fly zones or buildings and other things like this, even like weather conditions. And also if the generated patterns intersect with the obstacles, we need sometimes to modify them. So, for example, we can move the patterns, or we can create different patterns to deal with obstacles. And then also obstacles make the tracking phase more complicated because, of course, going from one location to another has to consider whether the path goes through an obstacle, and we are currently using visibility graphs to deal with this. This is just a screenshot of the simulation with obstacles. And now just conclusions. So we have presented a way to see search and tracking as a combination of reactive tracking and a deliberative search phase managed through planning. And we have tested successfully our planning strategy, and we see a number of benefits in this. Of course, all the benefits linked to using a generic planning technology that provide flexibility. Also, the behavior of the UAV is predictable, as I said before, and also a plan can be seen as a common medium of exchange of information between the UAV and a human observer that can be part of a search and tracking mission. And so our long-term research plan is to consider evasive behavior for the target, which of course will make things much more complicated, and then also to consider a multi-agent scenarios with multiple UAVs and multiple targets, and then to replace the fixed policy with a plan-based policy learning approach. Okay, thanks.